Hi, everyone. It's 2 o'clock. Welcome to today's webinar hosted by the Social Science Data Analysis Network, also known as SSDAN, which is housed in the Population Studies Center at the University of Michigan. While we get started, I want to highlight that in the email you received today with the connection information to the webinar, we linked to resources that will be useful for today's webinar. If you haven't already, please open a browser tab with the URL shown on the current slide. Today's webinar is on spatial analysis of US Census data in R and is presented by Dr. Kyle Walker. I'm John DeWitt. I'm here with the University of Michigan and Brookings Institution demographer William Fry, who's also founder and director of SSDAN. Before we begin, I want to point out two quick housekeeping details. First, the links provided on this first slide can also be found in the chat shortly. These resources will be helpful for Dr. Walker's presentation. Second, the 3-hour webinar will be split into 3 one-hour segments. Toward the end of the first hour, there will be an opportunity for some Q&A. Please feel free to use the Q&A function to submit your questions ahead of the Q&A session. Next, I'd like to turn things over to Bill for a moment to speak about SSDAN.
Thanks, John. JP, we're really pleased to have you today for our second webinar of our monthly March webinar Thursday series. Today with the spatial analysis using R with Kyle Walker. The Social Science Data Analysis Network is at the University of Michigan Population Studies Center, part of the Institute for Social Research. We've been for now over 25 years providing workshops and webinars and a website that will allow teachers and instructors and researchers to download and use and have easy accessibility to census and American Community Survey data for their teaching and for their research. And we're pleased to do these webinars during the pandemic. Our resources include classroom learning modules, data sets, guides to graduate programs in the population sciences, and there's much more if you go to our website, ssdan.net, to learn about our project. Our project is being funded by NICHD, and we appreciate their funding over time. So welcome to this webinar today. I do want to say that we have still a few more webinars after today in the month of March. Next week on March 18th, we're going to do something a little different than access to R, but it's called Integrating Data Analysis into Undergraduate Courses. This is not as sophisticated as an R-type analysis, but it allows people to look at all of the resources we put up on our SSDAN website, data sets, course modules, with people who are used to integrating these kinds of data into their courses. And so you'll be able to learn how to do that if that's something you're interested in doing. And then again, on the 25th of March, 2 weeks from today, we come back to our R series with Kyle Walker and analyzing US Census microdata with R. You can register for each of these by going back to the resources page that you were shown earlier. And, if you register for any of these workshops, you will get all the information, the links and so forth ahead of time, so you'll be able to participate. So with that, I'm going to turn it back to John DeWitt.
Thanks, Bill. Well, we have next up Dr. Kyle Walker, who's Associate Professor of Geography and Director of the Center for Urban Studies at Texas Christian University. He received his master's and PhD in geography from the University of Minnesota. Dr. Walker has taught a wide range of courses in geography, particularly human geography. He's also taught courses in data analysis and visualization using R, Python, and GIS. Outside of the traditional classroom, Dr. Walker has further created a virtual course for the Data Camp online learning platform called Analyzing US Census Data in R. He's an R developer who actively contributes to a range of packages, including some of those shown on the screen, and several he will discuss today. As an extensive stats user, I mentioned this last week, who has analyzed census data in SAS for more than a decade, I am always keen to learn more about how to use other statistical packages and other resources. And so I'm looking forward to what Kyle has to speak about today. I'll turn things over to you now, Kyle.
All right. Well, thank you everyone for coming out today. And thank you so much, JP and Bill, for the generous introduction, and the University of Michigan for hosting this webinar series, which I've been very much enjoying being a part of and getting the opportunity to share some of my work and some of the things that I've learned with all of you. So I'm going to go ahead and start the screen share and we can get things started. All right. So today's talk is broadly titled Spatial Analysis of US Census Data in R, with the subtitle Geometries, Maps, and Methods. And each of those sort of subtitles are what we're going to be focusing on today. You're going to learn all about US Census geometries, uh, boundaries, spatial data sets, and how we use them in R. You're going to learn how to make some maps using the fantastic TMap package for thematic mapping in R. And then we'll spend the last hour focusing on spatial data analysis. So for those of you who may come from a GIS background, say an ArcGIS or ArcMap background back in the day, like I did, you're going to see a lot of parallels here. And I'm going to walk through how to do a lot of common GIS type tasks using R, using code, and using some of the data resources that we're covering here today. So before we delve into the content, a couple of things. In the email that you received, and also JP had this up on the screen, you can also search for me on GitHub and you'll find it. If you want to follow along today live, there are a couple different ways to do that. One is to go to the GitHub repository for this series of workshops and grab the code for the workshops from there. If you're an advanced or experienced GitHub user, you can clone the repository in the spatial analysis folder, and you'll see a part that you'll take that. Alternatively, you click the button here and just download. If you're new to R, you might consider using the RStudio Cloud environment, and you'll access that by following the link that you received. If you participated last week and used RStudio Cloud, you may need to set up a new project, because I've loaded some new packages in there and I've loaded some new code. The code file that you're looking for is this spatialanalysis.r code file, and that'll include the code you need to get started. These packages that are mentioned in the code, they're already pre-installed in RStudio Cloud. So if you're following along at home on your own installation of R, you'll need to install those packages. There is a developmental package that I was not able to successfully install on RStudio Cloud. That's just a minor example, but I will give some instructions in a little bit for how to set that up on your own machines. So with that in mind, go ahead and get your environment set up if you'd like to follow along, or you can come back to it later and we'll get started. So thanks again, JP, for introducing me. Just a little bit of extra information. Again, I am an associate professor of geography at TCU. I also work extensively as a spatial data science consultant, working with individuals in a variety of organizations, and working largely on R-based projects. My passion in recent years professionally has been working on open source software, and you'll be learning today about a couple of those packages, tidycensus, which we covered in the workshop last week, but also tigris, which was really my first R package that interfaces with the US Census Bureau's Tiger line shapefiles, and we'll talk about that more in a bit. One of my most recent endeavors is Mapbox API. I'm a heavy Mapbox user in my work, and Mapbox API is, I think, a fun package to consume Mapbox services in R and allow you to bring that information in and use it in your R projects. I'm also actively working on a book. It's going to be an open book, and that I'll post on my website, and also will be published with CRC Press. finishing that up this year. It's been years in the making, but it's coming, and you're getting a sneak preview of the book's content. So everything that you're learning today, that stuff that's coming out of the book. So if you want to learn more, stay tuned. As far as the agenda with respect to the workshops, today's all about spatial analysis and mapping in R. If you missed last Thursday's workshop, and I imagine some of you are new, some of you were able to make it last week. If you missed last Thursday's workshop, if you have the slides up, and the slides are linked in the GitHub repository and in JP's email as well, you can go ahead and take a look. We talked all about how to get up and running with the tidycensus R package for acquiring and analyzing and wrangling US Census Bureau data. And also the talk was video recorded, so you can watch at your leisure and at your pace. Next Thursday, check out that webinar. It's not me, but it should be very, very interesting, thinking about integrating census data into undergraduate courses. I'll be back in 2 weeks on Thursday, March 25th. We'll be focusing on working with US Census Bureau microdata with our tidycensus, focusing on some new functionality in the package. And in the third hour, we'll have some bonus material as well, which I'm looking forward to presenting. So as far as today's agenda is going to go, and this is something that you can think about as you're preparing kind of how you interact and engage with this workshop. It's a 3-hour workshop, so we'll be going up until 5 p.m. Eastern time. So if you can only stay for part of the time, or if you want to leave and come back, we're going to try to organize it as best as possible by hour. So this first hour is going to be all about an introduction to census geometries and the tigris package, which I wrote to allow for the use of census geometries in R. Hour 2 is going to focus on mapping census data in R. And then finally, hour 3, which will start at 4 Eastern time, will focus on GIS workflows and spatial analysis of census data. So we'll try to start each of those hours on the hour. I'm not going to go a full hour for any of the hours. We're going to end probably at about 10 to 15 minutes to the hour, so that you have an opportunity to try the code out for yourself, do some exercises I've set up for you, and also ask some questions. And we'll do a little bit Q&A as well. We'll work that in. So keep that in mind if you're not able to make it for the entire time. All right, so getting started, an introduction to census geometries in the tigris package. So we covered this last week, but I'll reiterate here for those of you who are new this week. When we work with US Census Bureau geography, there are a lot of geographies at which we can get US Census data in aggregated form. The core hierarchy of census geographies you can see along the vertical central axis of this diagram. You start all the way down at census blocks. Census blocks are in some cases, say in a dense city, analogous to a city block, and they're the smallest geography at which census data are made available in the decennial census. Census blocks nest within block groups, which are the smallest geography at which American Community Survey data are made available. And then those nest within census tracts, and then counties, states, all the way up to the entire United States. Outside of that, there are a variety of different census geographies that don't necessarily nest within one another. You might have zip code tabulation areas, which are designed to approximate the geographies of zip codes. You have core-based statistical areas, which are akin to metropolitan areas, and then other geographies like congressional districts or school districts. And in turn, what census allows us to do is get not just demographic data that's aggregated to these different geographies, but actually the geographies themselves. And census releases a wide variety of shape files, which we'll talk about a little bit more in a moment, that integrate very, very well into all sorts of different US Census Bureau-based projects. The data that we're going to be working with come from the US Census Bureau's Tiger Line shapefile database. And Tiger, you see here, the Tiger logo, this is the Tiger Line database logo from the Census Bureau website, stands for Topologically Integrated Geographic Encoding and Referencing database. And so by topologically integrated, what that means without getting too technical is that you can ensure that the data are of high quality and kind of topologically correct, which means that they are connected to each other appropriately. And the US Census Bureau uses this information in concert with its master address file, which is not public information, to guide all of its enumeration efforts and then tabulate up its data that it releases to the public. And so the Tigerline shapefiles are very, very high quality series of shapefiles and geographic data sets released by the Census Bureau. If you're not familiar with the term shapefile, just to explain briefly what that is, a shapefile is arguably the most common vector geographic data set. I'll explain that a little bit more in a moment, but it's the most common, maybe the most common type of geographic data set that you're going to come across. Originally developed by Esri, but it's really widely used and to distribute geographic data. And shapefiles themselves are comprised of, or at least composed of, several related files. You have geometries and you have attributes, and you might have a projection file or some index files. Generally speaking, in a typical GIS workflow, you're going to do a number of different things. You're going to have to figure out, okay, where am I going to get this information? And typically what we'll do is we'll jump over here to the US Census Bureau website. So here I am on the Census website. This is the Tigerline shapefiles website. And you can see that the Census releases these shapefiles every year. They have a web interface, which you can click on, and it has a variety of different drop-down menus you can walk through. The 2020 Tigerline shapefiles are now released, corresponding to the 2020 decennial census. Let's say I want census tracts. I can click submit, and I can choose potentially a state like Florida. And if I were to click download, I download all of that information to my computer as a zip shapefile. What I would then do is unzip the shapefile and put it in a folder of my choice and open up a desktop geographic information system of choice. So I learned ArcGIS and ArcMap when I was first starting with GIS. Typically today I'll turn to QGIS. Some call it QGIS. I like to spell it out, but that's what you see here on the screen, which is a free and open source desktop geographic information system. And you can read in the data, and if you're familiar with GIS, this will look familiar. If you're not, it's an integrated interface that allows you to view spatial data, query it, do analysis, and ultimately make maps. So desktop GIS software is very, very useful, and it really can do all sorts of different things for working with spatial data. But you might be thinking, that's great. What if I want to stay in R? Can I do all of this stuff in R? And the answer is absolutely you can. And that's what we're going to be going through today. My typical workflow, being a population geographer, was sometimes on a daily basis going to that Tigerline website, pulling down data, saving it on my computer, and bringing it into a GIS and doing my work, whether it's data analysis or mapping or preparing materials for labs for my students or demos in teaching. I was always on that website grabbing data. And back in 2015, as I was really starting to shift my research workflow to R, I was dabbling in it at the time, but still using mostly Stata and ArcGIS for my actual analysis when I was writing research papers. I started thinking about, are there more efficient ways potentially to automate this process? It wasn't necessarily the most sophisticated process or really complicated process to have to go to the census website and pull down the data, but it was tedious, really tedious to go and click around and download and unzip and then load it in. And I was doing this over and over and over again. So I started experimenting a little bit with writing some scripts in R to download data directly from the census website. And indeed, something that if you've only used the drop-down menus, you may not be as familiar with. There's a web interface to the Tigerline shapefiles and also an FTP archive. And if you click there, you'll see a directory of all of the shapefiles at all of these different geographies. it's not always directly intuitive what these mean if you're not familiar with census geographies. But here I look at census tracts, and now I have all of these zipped tract shapefiles organized by state, specifically by FIPS code. If you recall from last week's workshop, one of my main motivations for writing R packages was because I can never remember what these FIPS codes are. So I live in Texas, which is 48. And I've been at this for years and years and years, and I do not have them all memorized. Oregon, where I grew up, is 41, and that's maybe the extent of what I remember, besides Alabama being number one. So this is a process, and I thought, is there potentially a better way to do this in my own work? And so I wrote a few scripts to talk to to basically take a link from the census website, the FTP server, and download that shapefile into R, unzip it, and then load it in as an object of class SP, which was the main mode or model of representing spatial data at the time. Eventually, this turned into the Tigris package. I wrapped it up, read Hadley Wickham's book, R Packages, learned how to write an R package, and then our programmer and developer extraordinaire, Bob Rudis, who some of you may follow on Twitter, he saw the project, found it interesting, and really taught me how to actually make a functional package. He supercharged it, did better download handling, and added features to it that really, in many ways, form much of the core of the performance of Tigris today. And so Tigris, here's my attempt at making a hex sticker logo for the package. Tigris is named as such because I couldn't really think of a good name. Naming projects is really, really hard. For those of you who are developers, this will certainly resonate. And so I just took the scientific name for tiger. I thought about Pantera, but it was too much like the band. And I thought about, say, our tiger line, but that was kind of boring. So Tigris it is, that stuck. And what Tigris allows you to do is, through a series of functions and a single line of R code, you can pull in custom extracts of US Census Bureau geographic data into your R environment. There's no API key required to use Tigris. You just install the package and you get moving. So let's take a quick look at how this works. Tigris has a lot of different functions in it. And what you'll do is you'll find the function that corresponds to the census geography that you want. And potentially you'll identify a state or a county, and you'll pull in that information. And so I'm going to jump over to R and we can see how this works. So here I'm loading in the Tigris package, and I'm requesting counties in the US state of Oregon with the counties function. I specify state equals OR. Again, this was something that was really important to me, to be able to say, I want counties in Oregon. I don't want to remember what the FIPS code is, because I'm never going to remember what those are. And so let's go ahead and run this code through and see what we get. You'll notice here that we get a little download bar. What that means is that our package here, what Tigris is doing is it's communicating with the census website. It's pulling down a census shapefile, which can take a little bit of time. And I'm going to talk to you in just a little bit about how to improve on that and avoid those long download times. But it's downloading that census shapefile into R. Once it's done, it unzips the file, it reads it in as what's called a simple features object, which I'll explain in just a moment, and gives you back the data. So what we have here going on is I have a simple feature collection, which is a model of geographic data in R, and it looks a lot like a regular R data frame. I have a bunch of rows and columns. Each row represents a county in Oregon. And then notably, I have a geometry column. That column is going to be important for us to understand. It tells us what the type of the spatial data set is. It's a multi-polygon which we'll get into a little bit more in a moment, and it encodes all of the coordinates that make up the data set. Now I have a counties in Oregon data set that I can work with. I can use the plot function in R, and I'm going to run that through to plot my counties, and there we go. I have all of the counties in Oregon that I can display on a plot and potentially use in my mapping projects. Jump back up here. So what was it exactly that we were looking at? You're looking at a simple features object, which is implemented in the SFR package, which in my opinion has absolutely revolutionized the way that we can work with spatial data programmatically. The SF package came out a few years ago and implements a simple features data model for vector spatial data in R. And if you're not familiar with GIS terminology, vector spatial data you can think of as points, lines, and polygons, discrete geographic features that are bounded. So a county is an example of a polygon. It's a bounded shape that has area. You can also represent vector data as lines. So lines don't have any area, but they have length. We use lines to represent things like roads and rivers and railways oftentimes. And points don't have length or area. They represent a specific location. Vector data is often contrasted with raster data, which is continuous spatial data. We're not getting into that today. Our census geometries that we're focusing on here are vector data. So the SF package allows us to do a wide range of things with respect to GIS type tasks in R. This first hour, we're just focusing on the data model and data handling. But as we saw when we looked at our data over on the R side, we get a sense of what a simple features object looks like. We have what looks like a regular R data frame here, where I have columns like state codes and names and the area of the land area and the water area. But also what's significant here is that geometry column. That is the key innovation here that the SF package is bringing to R. It allows us to store the shapes, because if you basically played connect the dots with these different longitude, latitude coordinate pairs, you would get the shape of each county. It allows us to handle spatial information right inside of a regular looking R data frame, which enables all sorts of workflows that were either more complicated or not previously possible. We have some other information. We have geometry type. So multi-polygon is our geometry type. Multi-polygon is slightly distinct from a polygon. It means that it can have polygons that aren't necessarily part of the same shape, but belong to the same entry. For example, a county that has islands would be a good example of that. And it has a bounding box, so kind of the minimum and maximum X and Y coordinates. And it has, in this case, a CRS, or a coordinate reference system, which we'll get into a little bit more in just a moment. What this allows us to do is we can plot the geometry column. We get that plot of counties in Oregon, and we can really just get started bringing in geographic information to our projects very, very quickly. There are a wide variety of data sets that are available in Tigris. And if you go to the Tigris documentation on GitHub, you'll get a full listing of all of the functions that are available in the package. Something that you also might consider doing if you're interested is going to the help documentation for Tigris. And so if I go to my packages pane in our studio, I search for Tigris. I can pull it up here and I can see all of these different functions that are available, many of which are geographic data sets that I can grab. If I want census designated places, I use the places function. If I want school districts, I use the school districts function. If I want, say, state legislative districts, I use the appropriate function. data sets available in Tigris fall into one of three different categories that are provided in the Tigerline database by the US Census Bureau. The first is legal entities. These are going to be geographies for US residents that are probably going to be the most familiar. They're bounded units that have legal significance in the United States. So for example, states or counties. Those are geographies at which the US Census Bureau tabulates data, but they're also geographies that have legal standing. They have actual boundaries and governments that govern them and that sort of thing. Statistical entities, by contrast, are similarly geographies at which the United States Census Bureau tabulates data, but they don't have legal standing, generally speaking, in the US. A good example would be a census tract or a block group. We use those analytically all of the time because they're salient geographies at which the Census Bureau tabulates information, but the actual boundary of a census tract does not have any legal meaning per se within the US context. And again, most Americans don't know what their census tract or their block group is. The third type of geographic data that is available in Tigris from the Census Bureau are geographic features. These are not going to be geographies at which census data are tabulated or aggregated, but there are other data sets that are often very, very useful for thematic mapping and indeed even spatial analysis. This includes roads, it includes linear and area water features. These are data sets that you can grab in Tigris and you might find very, very useful to have in your projects. So taking a look at some of these different types of data sets, let's look at a statistical entity here. Census tracts. This is actually the county in which I grew up in Oregon, Benton County. And we can use the tracts function to pull down a tracts shapefile for that specific county and then load it into R. And so going back to R, let's take a look at how this works. I run the code, I pull it down, and I get my census tracts. I can view them here. We can also grab linear features. So we see here with our Benton census tracts, if I print that out in my console, I can see that this is a geometry type multi-polygon. What I'll do here now is grab roads for Benton County, Oregon, and plot the result. You'll see here now I get road data. You see around the various cities of Benton County. It's a mostly rural county, but the city of Corvallis is a little bit denser. You can see that road network. And if we print that out in our R console as well, you see that it's a little bit different. Our geometry type is line string, and we have the name of the road. Sometimes you'll have different line segments that correspond to the same road. But those lines, again, if you play connect the dots with these longitude-latitude pairs, you'll get the shape of that line segment. Finally, and there aren't too many point data sets in Tigris, but one is landmarks used by the Census Bureau to assist enumerators in the field. And you can get that information with the landmarks function. So I can pull down landmarks here in the District of Columbia. I say type equals point to grab point landmarks, and I can plot that. And you see here represented as dots on my plot. These are specific locations in Washington, D.C. And I can print out that information too if I want to. And I see that my geometry type is point. And here I have a variety of different landmarks. It looks like we've got the Washington Monument, the Lincoln Memorial, the Jefferson Memorial, and a variety of other places that are likely familiar to many of you. So those are the basics of getting started with the Tigris package. How is this all working under the hood? I've explained it a little bit, but let's go into a little bit more detail. The whole process that you would typically go through when you're working with US Census Bureau shapefiles, I mentioned before. You go to the census website, you go through the drop-down menus or the FTP website, you find the appropriate file, you pull down that file, save it somewhere, unzip the file, find a program in which you can load it, and then get to work. A single tigris function call does all of this for you, and it does it in a single line of code. And so there are a couple different ways that you can go about storing those files. You saw that downloading that counties file, it took a little bit of time. For very large shape files, like block shape files, say you wanted to grab blocks for the entire US state of Texas, of which in the 2010 census, there were nearly 1 million, that's going to take a long time. I recommend using this option, tigris use cache equals true. If you run that code, and some of you may have seen me do that already to speed up my presentation, if you run that line of code before you get started with tigris, it instructs tigris when downloading the shape files to store them in a user cache directory that gets set up on your computer. And then when you're using caching in the future and you set that option, tigris won't go to the census website to download the data set if the data set already exists. If it already exists on your computer, it'll grab it from your computer instead, meaning that you don't need to worry about download times at all. So this is entirely up to you. If you're working on a shared computer, if you don't have access to the file system, this may not be a good option for you. But if you're working on your own computer or you have access to the file system, this is what I recommend. It's not the default option because you're not allowed to do that by CRAN policies if you have a package up there, but it's the option that I recommend. So let's talk a little bit about some additional features and options you can use in tigris to really supercharge your work a little bit. I got this question a lot when I first started working with tigris. Why does Michigan look so weird? And so, we're presenting this for I'm presenting this for the University of Michigan today, so it's germane. But this is a pretty normal query I would get. Someone would email me or post on GitHub. I downloaded data from Michigan, but it looks like a big blob. That is not what Michigan is supposed to look like. You have the Upper Peninsula and you have the detailed boundary around the various Great Lakes that surround Michigan. And instead I've got this big blob. What's going on? Well, this is what Michigan looks like by one definition. The core tiger line shapefiles include water area off the coastline. So if a water area belongs to those counties, as you can see here, then it's going to be included as part of the shape in the core tiger line data set. And we can run that through over on the R side and take a look at that when we plot the geometry. You'll see that here. So that's useful in as much as what the actual extent of those counties are, water and land. But at the end of the day, if you want to make a map of counties in Michigan, that is rarely what you want to use. You want to have something that just represents the land area, cleanly shows the Upper Peninsula, and it looks a lot more like what people will expect. To do that, tigris pulls from a separate data set called the US Census Bureau's cartographic boundary shape files. All you have to do is specify the argument CB equals true. For data sets for which cartographic boundary files are available, you can get that instead of the core tiger line shapefile. And so if you want to make a map, which we'll be doing in hour 2, that's what I recommend using. You can get highly generalized shape files if you want to make interactive or small scale maps where you're really zoomed out. That's a great option. The cartographic boundary shape files, they are clipped to the US shoreline and they're generalized in the interior so that they display faster. This is what tidycensus, by the way, uses by default. It uses the cartographic boundary shape files, though the core tiger line shape files in tidycensus, which we'll talk a little bit more about in hour 2, can be obtained if requested. So you see here on the slide, let's run that through in R as well. By setting that option CB equals true, we get a plot of Michigan now that looks a whole lot more like what we would expect and what we probably want to use in a mapping context. Some additional features in tigris that you might be interested in. The US Census Bureau releases shapefiles going back to 1990, and tigris supports shapefiles going back to 1990. Now, granted, you can't get all the data sets back to 1990, And Tigris has to do some internal cleaning and harmonization of the old data to get it ready to go in a capacity that you want it. But what we can do here is we can grab, say, census tracts over time. The 2020 shapefiles were just released. And so we can take a look at those geographies in comparison with, say, 2010, 2000, and even 1990. I mentioned here on the slide, legal entities change shape fairly rarely. They do change, however. I'll show you an example in a moment. But statistical entities, they change every decennial census. And so census tracts, for example, are designed to have about on average 4,000 people, give or take. And so if you have an area of population growth, those census tracts are going to be subdivided up for the next census. So I'm going to pull here cartographic boundary shape files for 1990, 2000, 2010, and 2020 for the county in which I live, Tarrant County in Texas. If I run that through and then use the code on the next screen here, I can make a 2x2 plot and compare those geographies. And as you can see, in 1990, especially in the northern part of the county, you have census tracts that are geographically very large. By 2020, that whole area along the Interstate 35W corridor has been developed and built up, and the Census Bureau has subdivided up that area into multiple census tracts. And so on the R side, you can go ahead and run that through. You'll notice I put here a suppress messages command in my code, which I pushed up to GitHub right before the workshop. There's some internal data processing that's printing out some messages. And in the next release of Tigris, those will be suppressed internally. I'm going to run that through, grab my yearly data, and make the plot. Now this plot, it's informative. I could fiddle around with the zooming, but one thing that's a little bit tricky about it is I can't interact with this information. And honestly, when I first started really focusing on doing geographic data analysis and visualization in R, this was one of the main reasons why I would still go back over and over again to my friendly desktop GIS, either QGIS or ArcGIS. The ability to interactively browse my data sets, click on them, get information back. For me, that was such an important part of the exploratory data analysis process, and I simply couldn't do that in R. But the beautiful thing about open source software is that if there's an issue like that, likely someone is already working on it and trying to resolve it. And indeed, it's been resolved in a stellar way with the MapView package. The MapView package is a phenomenal effort that allows for quick interactive mapping of spatial data in R. It wraps the Leaflet R package, which I don't demo in great detail in this workshop, but I recommend you check out. It's one of the most popular packages in R for interactive spatial data visualization, which is an interface to the popular Leaflet JavaScript library for web mapping. MapView sits on top of that and allows you to pass a spatial object to the MapView function and display an interactive browsable map right in R Studio, and you can get going visualizing and exploring your data right away. So let's take a quick look at how that works. I'm going to load the MapView package. I'm going to map view my Tarrant County 2020 census tracts. And here I have my interactive map. I can zoom in. I can take a look at all of those census tracts up in northern Tarrant County. I can click on a tract and I can get a pop-up that's nicely formatted and shows all of the information that's available in that particular data set. If you want to go further than this and make comparisons, one of my all-time favorite packages in R is the Leaf Sync package, which allows for synchronized mapping of multiple maps interactively. All you have to do by using the Leaf Sync package is use its sync function with 2 or more maps. And so here I'm syncing up a map view of Tarrant County in 1990 and Tarrant County in 2020. Take a look at what I get back. I get an interactive map where, as you can see, my cursor's over on the left-hand side. I get a red circle on the right-hand side. And if I zoom into this large census tract in the northern reaches of Fort Worth, you can see that this giant census tract in 1990 has now in 2020 been divided up into more than a dozen census tracts. It allows for really interesting interactive comparisons, which is pretty exciting when you're doing exploratory analysis of different geographies. I mentioned this before too. One thing that's interesting that you can see with LeafSync, if I zoom in way up here, look at this area where my cursor is, and then where the red circle is on the left-hand side. I mentioned that legal entities rarely change, but sometimes they do. This isn't a data error. I actually discovered it when I first started teaching at TCU, and I didn't know much about the local geography. So there was a legal dispute between Tarrant County and Denton County, in which Tarrant County argued that this little slice of area you can see highlighted on the screen actually should belong to Tarrant County and not Denton County. And the judge ruled in its favor. And in turn, that little slice was ceded to Tarrant County. And so if you go back to older data, like here in 1990, you'll see that parts of Denton County at that time are now part of Tarrant County. Local particularities like this do exist, and they have downstream analytic implications. So just an interesting example to focus on. A few other applications to go over before we break. I had a few questions last week about, well, how do I get a data set for the entire country from tidycensus? And I said, well, there's some ways to do it. You want to look at the per package, which is part of the tidyverse, and iterate through a bunch of data sets and combine them. This is a little bit more cumbersome in tidycensus than it is in tigris. If you need a national data set, say of census tracts or block groups, as as analysts we sometimes do, this code will get you there. What I'm doing, and I'm not going to go and run through this code, but you're welcome to. Just be prepared. You're going to need to do a little downloading. But I create a vector of state codes here, where I'm combining the built-in state abbreviations vector in R and DC. And then I'm using the mapdf function from the tidyverse. It's a little bit more of an advanced example here, but just to translate what this is doing, it's saying iterate over all of the state codes in the United States. And for each of those state codes, run the block groups function, grab the cartographic boundary file, return it as a simple features object. And then what the mapdf function does is it assembles everything back together into a data frame. And what that gives me back, and if you have all of these data sets already cached on your computer, it goes pretty quickly, is all of those block groups in the United States combined together into one data set. The last little piece that I want to mention, and this is a big topic that unfortunately I don't have a tremendous amount of time to get into in great detail, is the coordinate reference system. For those of you who have geographic data analysis experience, you've likely spent quite a bit of time grappling with coordinate reference systems, which I'll refer to as CRS or CRSs, which in general terms refer to the way that your spatial data are referenced to the Earth's surface. So we have a data model, and we have a model of the Earth's surface, and we need to know where the different coordinates in our data go relative to that model of the Earth. That's what the coordinate reference system does in, I would say, simplistic terms. For any of you who have taken a GIS course, you spend a whole lot more time on this. So a couple distinctions that are important for you to know about if you're working with spatial data. We'll encounter geographic coordinate systems which represent coordinates as longitude and latitude. So thinking about a spherical representation of the Earth, and projected coordinate systems, which you'll commonly use if you're doing local analysis or you need to represent geographic data in 2 dimensions, so on a plane. The units of measurement are going to be different. So in a geographic coordinate system, you'll be working with decimal degrees, most likely, longitude and latitude. Whereas in a projected coordinate system, you'll be working with meters or feet, units of planar measurement. So by default, the US Census Bureau stores tiger line shapefiles as in a geographic coordinate system using the North American datum of 1983. EPSG is, well, I'll talk a little bit more about that in a second, but every coordinate system, or just about all of them, have what's called an EPSG code, and it's a maybe 4, 5, or 6-digit code that uniquely identifies that coordinate system. And you might be thinking, well, why do I need to know about all of this? If you're working with kind of local areas, if you're working with data and you want to represent it in an appropriate way, understanding an appropriate map projection is going to be important. So that you can make accurate, say, distance measurements, area calculations, or just make your maps look better. And so this is a hard topic to wrap your mind around. You can get a little bit more information about that CRS using, in the SF package, the ST-CRS function. Here's counties in Florida, and this is a representation of what's describing that coordinate reference system. If you want to get into this further, and apologies on our Studio Cloud CRS, this package is not running, but I am in the process of developing the CRS suggest package, which again, all of my R packages are basically to help me do things that I find painful or frustrating. And I started writing this package about a year ago to help pick out the right coordinate reference system for your data. It's installable from GitHub. So basically, if you're new to R, you generally install packages with the install.packages function, which pulls down packages from CRAN, which is the central repository for R packages. Many other R packages exist on GitHub where developers will host their code, and they won't necessarily be published on CRAN. And you can use the remotes package with the install GitHub function to install those developmental R packages. What CRS Suggest does as a package is it includes some custom code under the hood to try to take your spatial data set and match it up as best as possible to an appropriate projected coordinate reference system that you can use. The Suggest CRS function, which I'll show you here, goes through and identifies the best possible, the best matching coordinate systems that you might consider using and gives you information back about it. And so if I run that code through over on the R side, I'm going to go ahead and pull down that Florida data and suggest some coordinate reference systems here. Need to load tidyverse. Take a glimpse here. And here I have a bunch of coordinate reference systems I might consider using. The top choice here is the Florida Geographic Data Library, ALBERS, with CRS code, which is that EPSG code 3086. This is a coordinate system that is designed for representation of the entire state of Florida, and Florida being, having the panhandle and then the rest of the state, and even crossing over multiple time zones, a very local coordinate system might not work well for the whole state. Texas is the same way. Texas has statewide coordinate systems as well. So you could grab a code from here and then pass it to this ST transform function, which will do a coordinate reference system transformation on your data and project it, if you will, to a different coordinate system that you can use in your analysis and your mapping projects. And so I can run that through. And what you'll notice here is that I have a new projected CRS for my data. It's the one that I chose. And my geometry, you'll notice those are still longitude and latitude coordinates, but they're not decimal degrees, or I should say they're still X and Y coordinates, but they're measured in this particular case in the measurement units of the coordinate reference system, which is meters. There's a whole lot more we could talk about with respect to coordinate systems that's beyond the scope of this talk, but it is a topic that if you're working with spatial data, you'll want to know about it. And hopefully CRS Suggest can help ease the pain of figuring out which coordinate systems to look at. So let's go ahead and stop there for hour one. We'll take maybe a 10-minute break and come back around 5 past the hour so we can keep things moving. Use that time to get up and stretch as I will, but also try out Tigris for yourselves. I've linked the Tigris documentation here. Look at the geographies that are available and pull down some geographic information, maybe for a county or a state that you're familiar with, and try plotting it either using the plot function as we've done, or try out the map view package and interactively browse that data. So spend a few moments doing that, and let's start up again in about 10 minutes. We'll do a little Q&A and talk about mapping data in R. All right, welcome back, everyone. Hope you had the opportunity to try out Tigris for yourselves, play around with it a little bit, and that sort of thing. We have a few questions from the Q&A that we're going to go over briefly before we get started with the next section.
Yeah, Kyle, we've had a few questions come in, and we'll try to get to as many as we can, but there have been a good number of them. So some of them we may have to follow up after the session. But the first question I have for you is, does the cache option check the server for an updated version of the file?
So the files themselves shouldn't change. They will change yearly, and that'll be designated by that year option that I demoed how to use in Tigris when you're pulling down those files. But the files themselves, once they're uploaded, those should be the files. So basically, you're downloading that file to your machine, or you're pulling it down from the website. There are ways, if you want to, that you can go in and you can clean out your cache directory. So if you, what we do in Tigris is we use the raptors package. And so that is installed on your machines. And you can identify what your cache directory is. In fact, if I go over to R here, I can show you. If I run this code here that I have on my screen, where I'm pulling from the raptors package, I'm saying, what's the user cache directory for Tigris? It'll tell me what that directory is, and I can navigate there and I can remove shapefiles if I want to. So if you're getting a big repository of shapefiles on your computer and it's clogging up your hard drive, you're more than welcome to do that.
So somewhat related to, I think, the caching and getting a number of geographies. Someone asked, can you repeat what state equals .x is doing? You have that in your code. It's off the screen now.
Yeah, so let me pull that up. This is a little bit more advanced, and this is using notation from the tidyverse. So I want to have that as a caveat. This is really for power users who want to exploit some more advanced functionality within the tidyverse and the Tigris package. So walking through again what this is doing, and I'm actually going to pull this up in R so I can show you all. What we're doing here with this code is we are iterating over all of the states in the US plus DC and grabbing data for each of those states for block groups and then combining the result. So I'm going to run this through real quick and show you what this object state codes looks like. Those are all of our different state codes, including DC. When I run any of the map functions in the tidyverse, you can read this as map over or iterate over this object. So do something once for each element of this object. So do it for Alabama, do it for Alaska, do it for Arizona, et cetera, et cetera. We're using here formula notation, which is one way of expressing this in the tidyverse, because what we need to do is set up something such that the mapdf function understands what it's going to do for each of those different state codes. And using the formula notation, we get a local variable here called .x. .x, and this is a really good question, every time that we iterate through and use each element of the state codes, .x takes on that value. So if any of you, again, this is a little bit more advanced, but if any of you have used local variables within, say, a for loop, programming in R or Python or another language, that's effectively what that .x is. I can be more explicit about it if I want to and define what that's supposed to mean. There's alternative notation that I could use. And I would strongly recommend reading up if you're interested in really getting further into this, some of the materials that our studio has put out about functional programming within the tidyverse. But in this particular case, you can think of this as, here's my process. Okay, find the first element of state codes. It's Alabama. Now run block groups for state equals Alabama, CB equals true. Hold on to that object, store it. Now go to the second one. Run it for Alaska. Get the block groups where state equals Alaska, CB equals true. Store that too. And it's going to run through each state until it has all 50 states plus DC. And then once it's done, the mapdf function knows to reassemble that back into a data frame, which in this case returns a simple features object of block groups in the entire United States. So that's what's happening under the hood here. And part of the reason why I would recommend for those of you who are looking to get a little bit more advanced with R, if you haven't used the PER package before, instead of having to go through and pull down this information one by one, we can express this in a couple lines of code and get all 200,000 plus block groups in the United States combined together. So it's very handy once you get the hang of it.
All right, and we have one other question that you already kind of touched on with, I think it was Tarrant County, Texas, but we have a question that is, my understanding is that census blocks, block groups, and tracks are updated with the decennial census. Why are there annual releases?
That's a great question. They are updated with the decennial census at large scale, but there are often minor tweaks that occur between censuses. And there are a variety of reasons for this. One is, occasionally, very rarely, but occasionally census tract boundaries do change slightly. Census tries to align tract boundaries with major geographic features. And if there is, for example, some massive development where the old tract boundary doesn't make sense anymore, occasionally they will change it, though that's pretty rare. The other thing that can and does happen is counties will get new names and in turn new FIPS codes, and that'll happen between censuses. For example, a great example of this is Shannon County, South Dakota became Oglala Lakota County, South Dakota in between censuses and got a new FIPS code accordingly. And so all of its census tracts will then get new FIPS codes and new GeoIDs. And so, whereas if you go back to before that change took place, those census tracts will be named one way, then after the change will be named another way. And so basically, and this will be important for the content in hour 2, Tigris aligns with information that's coming out from the census as best as possible. So at the moment, Tigris defaults to 2019 shapes. So if you want 2020 shapes that just came out, you'll have to supply year equals 2020 explicitly. I will keep it at 2019 shapes for the time being until the cartographic boundary shape files for 2020 are released. And so right now we don't have the full allotment of 2020 shape files. We don't have cartographic boundary shape files yet. So it's going to stay at year equals 2019 for the default until those are released. And then I'll go ahead and update it.
Great, thanks. I think that's all we have for questions for right now. We'll have more questions in the next hour.
Sounds good. Let's dive right in. One other kind of late breaking question a couple of you had asked who had visited for the previous workshop and wanted to use our Studio Cloud again today. The way I was seeing with our Studio Cloud is that if you copied over my project, your project is not going to automatically update from last time. So you're going to need to go back to the link and pull down and make a new temporary project. Unfortunately, that doesn't have your old work. It's not sort of a perfect solution, but I just tested it out, and I was getting the new code that way. So if you're using RStudio Cloud, you may need to make a second project that's a copy from the link that I provided, but everything else should be in there, and you can reconstruct what you did. All right, so let's dive into part 2, mapping census data in R. So we've talked about the traditional kind of census data acquisition process. Beyond that, you'll often want to grab other data that you can map and analyze. It's not just the shapes, it's also the attributes that are interesting, the demographics, the economic statistics. And so to get spatial census data, and we spent the entire workshop last week focusing on getting census data, but what about census data you can map? How do you do that? Well, typically you've got to go through the process we talked about before, fetching those shape files from the census website. So we pull that down and we get it. We then go to data.census.gov or another data portal, and we pull down an Excel spreadsheet or a CSV of data, and we clean that up and we format it. We then load both the geometries and the data into our GIS of choice. We might need to do some more internal wrangling of the data just in case, say, our CSV file is lopping off leading zeros or something like that. And then finally, we align a key field in our GIS. We may need to do some more transformations to get it just right. And then we perform a join operation, analogous to a join in a database, but ArcGIS, QGIS implement joins. And we join our data together. And then once we've done that, now we have our spatial census data that allow us to do analysis and make some maps. It's interesting in thinking about, originally my motivations for writing some of these R packages. When I first started teaching at TCU, I mean, my thing was exactly this process. This was my specialty. This is what I was publishing papers on, how I did my research. And I incorporated it directly into my brand new intro to geographic information systems course. They did a couple lab assignments learning about, how do you identify features in ArcMap and make a basic map layout, and now let's go map some census data. And I wrote this behemoth lab assignment where students went through that entire process, and their goal was to map poverty rates in our county, Tarrant County in Texas. It took them forever. It was such a painful process for them. They would run into all sorts of issues where, you'd load in the census shapes and the GeoID column. So the census ID code was formatted as a character string, whereas you load in the CSV and it's formatted as a number. And so you can't join because you have incompatible types. So they need to do type conversion. And for people new to geographic information, this adds up pretty quickly. And on the other side of that, this was something that I had gotten accustomed to just doing, but I found it very, very tedious. And so, back in 2016, 2017, I had this tigris package, which I was using heavily in my work. And I started developing tidycensus, which I talked about last week. And one of my top priorities, and really the reason why I wrote tidycensus, because there are other census packages out there that are very, very good. But really the reason why I wrote tidycensus was I wanted an integrated interface to give you back pre-joined geometry and attribute data in a single function call, a single command to do all of that whole process that sometimes, was taking my students hours to do. Just do it all in one fell swoop. And that's what, for me, my favorite feature of tidycensus is. So if you did not get the chance to attend last week's workshop, I do apologize if there's a little bit of a learning curve here because we don't have time to go all the way back through all of the stuff that we covered last week. I would encourage you to kind of jot down, what you can take away from this, and then go back to last week's video and fill in some of the gaps. But just as a basic overview, the tidycensus package, for those of you who are joining us for the first time today, is in our package that I wrote to interact with the Census Bureau's website and pull down and return formatted data from either the US Decennial Census or the American Community Survey and a couple other data sets. The way you do that is by using a function that corresponds to one of those data sets. And so, here I'm creating an object called DC income, where I'm grabbing median household income data by census tract for the District of Columbia. I'm using the getACS function to do that. And again, if this is your first workshop, if you didn't attend last week, that's no problem at all. Just follow along as best as you can, and take a look at hour 1 of last week's workshop, because there's a lot of information on there to get you going. So this example here, DC income, we can run that through, and I want to show you a couple things. I'm going to jump back over to our studio here, and I'm actually going to make another example so we can compare and contrast what we get. So I'm going to run DC income 2 times, once with geometry and once without geometry. I'll call the first one just DC income 1 so we can distinguish what we're doing. When I run that through, I pull down data from the American Community Survey, and I take a look at what I get back. And you'll see here that we have, as for those of you who have used tidycensus before or attended last week, we can see here we have our typical 5-column data structure that you get by default from tidycensus. You have our GeoID column, you have the name of the census tract, the variable, we're replacing the variable code here with HH income, and then we have the estimate and the margin of error around that estimate. Some census tracts don't have enough observations for a median household income estimate, so it's returned as NA. So that's what you get by default. I'm now going to run this through with geometry equals true. And let's see what we get back. Now when I print out the result, you'll notice I get a simple features object back, akin to what we looked at when we were talking about tigris. But what you'll notice here is it's not just geometries, like if I had gone and grabbed census tracts for the District of Columbia, but rather I get the census data along with it. So all I had to do was specify extra here, geometry equals true, and it gives me the geometry automatically. How does this work? Well, tidycensus wraps tigris. Tigris lives under the hood of tidycensus, and when geometry equals true is called, like we just did, tidycensus says, okay, tigris, go do what you do, get the data, give it back to me, and then I'm going to align it correctly to the census data, merge it under the hood, and give back a pre-joined spatial census data set. Now I can get started making maps. I can do some analysis, and we're going to learn how to do that over the course of the next 30 or so minutes. Indeed, if we want to start exploring our data, we can get going with that right away. We learned about the plot function for plotting census geometries in the first hour. What you can do is specify a column in your data that you want to plot, and the SF package, which wraps the base R plotting method, will give you back a map using this default kind of yellow to blue color palette. If you're familiar with plotting in base R, you can customize this map using all of that functionality. But if I go back to R and I run through that code, you'll notice that I've made a very basic but functional visualization of median household incomes by census tract in Washington, D.C. with a minimum of fuss. Last week, we focused heavily on the tidyverse and specifically ggplot2 for learning about how to work with and visualize US Census data. For those of you who didn't attend last week, that was the focus of hour 3. So I encourage you to go back and take a look at that information for some background there. ggplot2 also includes a special method for plotting simple features objects called geom_sf. This is, if you like ggplot2 and you're familiar with it, a fantastic way to get started with basic mapping, but also all the way up to advanced mapping with ggplot2. We use familiar ggplot2 syntax. Here I specify a data set and then an aesthetic. In this case, my fill aesthetic is going to be the estimate column. So my American Community Survey estimate. By specifying geom_sf, and I don't need to do anything else to get a basic exploratory map, ggplot2 interprets the geometry type of my SF object, sees what kind of map to make, and gives me back that map in just a couple lines of code. I'm going to run that code through here, and let's take a look. There's a ggplot2 representation using all the defaults, the default gray background, the default kind of dark blue to light blue color palette, and allowing for visualization of our data. So a couple of very quick exploratory maps are available with a quick data pull and a couple lines of visualization code. So if you're exploring your data visually, your spatial data visually, these are great ways to get up and running. Those methods, however, are not going to be the overarching focus of this second hour of the workshop. We're going to focus on a package called tmap. Tmap is an absolutely incredible effort to bring cartographic methodology to R, and it allows for near infinitely customizable maps. It is pretty incredible, and we're not going to get too complicated today. We're not going to get really deep into the functionality and methodology of tmap, but you can make beautiful publication quality maps that are really custom designed using tmap's very, I don't know if sophisticated is the right word, because as you'll see with a couple lines of code, we can get up and running with maps, but it's quite involved, the number of options that are available for you. And it was designed to perform thematic mapping in R, but also bringing a ggplot2-like syntax. So the way it kind of works with different layers and layers on different options is going to be familiar to people coming from ggplot2, but I also like tmap for people who are coming to R from, say, a desktop GIS. As the options that are available are going to be familiar to cartographers who come from ArcMap or QGIS. geom_sf and ggplot2 is fantastic, but it is using the syntax that's familiar to people who are already using ggplot2. tmap instead allows for thematic mapping in ways that, say, a GIS user is already going to be comfortable thinking about mapping and display of spatial data. And so it's a really nice example to get into in this particular capacity. So let's go ahead and grab some data. Again, we're using a couple different options in tidycensus that we covered last week. We're using the getACS function, and we're going to grab census tract level data for Hennepin County, Minnesota. Hennepin County, Minnesota, that's the county that includes Minneapolis and several of its suburbs. And we're going to grab race and ethnicity data from table B03002, which is Hispanic or Latino or not Hispanic or Latino by race. And so this allows us to get data on white, Black, Native, and Asian populations, but non-Hispanic in each case, and then also Hispanic of any race. And so we grab those columns, and we'll also get a summary variable, which is going to be used as a denominator to normalize our data. We'll pull geometry with geometry equals true, and then we'll use the tidyverse mutate function to calculate a new column, where we're creating a new column called percent, which is 100 times the estimate divided by the summary estimate. So in this case, for a census tract, the percent value for white will be 100 times the white population divided by the total population. We can take a quick glance at our data and we see what we get back. So here, for my first census tract, I have a name. The first variable is white. The estimate is we have about 2,900 non-Hispanic white people living in that tract with the appropriate margin of error of about 4,200 people overall. And so that census tract is a little under 70% non-Hispanic white. Let's run that through on the R side and pull that data down so that we can work with it. So let's go ahead and get started working with TMAP. We have data right now in long form. And so a couple things to go over here before we really delve in much deeper. I'm going to print out Hennepin race another way so we can just take a quick look at it. This is long form spatial data. We talked last week about the distinction between long form and wide form data. And I mentioned that wide form data is going to be more familiar to people coming from a GIS background. What I want to show you here is how to do some mapping methods with long form data, how to potentially work with long form data. And you might still end up wanting to use wide form data for what you're doing, but there are some certain things that can be done with long form data that are pretty handy when making maps in R. And so in this case, each census tract has 5 rows that correspond to it. So this first census tract has 1 row per variable, which is racial or ethnic group, and then corresponding information along those lines. And so we're going to start out mapping a single group. And we'll look at the non-Hispanic Black population in Hennepin County. What I'm going to use is the tidyverse filter function to filter down my spatial data set, filter down my tracks to retain only those rows where the variable value is equal to Black. To make a basic plot of my spatial data using TMAP, all I have to do is initialize the data with the tm_shape function. And then in this case, I'm using tm_polygons to plot the polygons. You'll notice that there are no arguments. That simply means that we're just going to show the polygons using the defaults here, which has a gray fill and a darker gray border. So let's give that a try. Here we have our plot. So from here, you might be thinking, well, I have all this data. Isn't the point to visualize it or maybe show the distribution of, say, a group or different groups? Of course it is. And TMAP really excels at getting you up and running, making quick exploratory, and then eventually explanatory maps of your data. We're going to go over in the next several slides a variety of different thematic mapping types. And if you're new to cartography or geography, a thematic map is a map that focuses on a specific variable of interest. It shows you the spatial distribution of a specific thing and doesn't focus on really anything else besides that particular theme. That differs from, say, a reference map. If you were to bring up, say, Google Maps on your computer or on your phone, that's a reference map that tells you all sorts of different things like traffic and points of interest and roads and lakes and rivers. A thematic map is interested in maybe one, maybe two things, and it's going to focus specifically on that. And that's what TMAP really excels at. One of the most common types of thematic maps that you'll work with is what's called a choropleth map. And choropleth refers to the display of statistical variation in your data using color or shading, where lighter or darker colors are mapped to particular quantitative ranges in your data. And, in turn, allow you to look at geographic variation in some of the attributes in your data. Choropleth maps should generally be only used with normalized data, like rates or percentages. They're not recommended for counts, in part because there's this potential, certainly, for the denominators of places to vary widely. It's very easy to, show a choropleth as sort of a shaded map, and it draws your attention to these really big areas. For example, those big census tracts out in northwestern Hennepin County, pretty sparsely populated, but your eye is going to be drawn more to it. And it's possible that there are more people living out there too than in some of the smaller census tracts. And so we're going to use our percent column to display variation. And all we have to do to make our first choropleth map is specify here col equals percent. You can put in either the name of a column, or you can put in a particular color if you want to change the color of your polygons accordingly. But in this particular case, TMAP sees that there's a percent column in my data, and then it maps that column to the default color palette here, where the darker oranges represent a particular concentration of a group. In this case, it's the non-Hispanic Black population, which tends to be more concentrated around Minneapolis's north side, near the University of Minnesota, and in the suburbs of Brooklyn Center and Brooklyn Park. These are the defaults. And let's go ahead and run that through just so we can take a look at it. These are the defaults in TMAP. You have sort of that orange, yellow-orange color scheme. You have a default cuts in your data where kind of the lightest yellow is 0 to 20, kind of the darker orange color is 60 to 80%. That gets you started visualizing your data, but you might want to make some modifications to this. You likely will change the colors, change the cuts. If you're coming from a GIS background, you may be thinking about, say, using quantile breaks or equal intervals or natural breaks. That's something that we're very familiar with in a GIS context, and TMAP allows for the use of all of that. And so we can look at a more customized map. Before we do that, I want to show you a really interesting feature to think about modifying these options. The palette parameter allows you to specify or choose a different color palette and map that to your data. The style parameter then implements various breaks methods. So equal interval, that means that the cuts, the bins, so to speak, will be at equally spaced intervals. Quantile breaks means that each bin, so to speak, will have the same number of observations in it. And we can also specify Jenks for the Jenks natural breaks algorithm, which looks for naturally occurring breaks in your data and puts the bin cuts there. And so here we're making a few modifications. We're specifying style equals quantile breaks, which means we're putting the same number of census tracts into each bucket. We specify n equals 7. We're changing the color palette to purples. We're giving our legend a title. We're giving our layout a title with the TM layout function, and we're moving the legend outside of the plot area. So hopefully you're starting to get a sense of some of the customization that you can do. Let's run that code through. And here we have a differently styled map. And with choropleth maps, you're probably getting a sense of that here. The choices that you make reveal or show important variations in your data. If we're just looking at cuts every 20% here, it looks like there are a couple concentrations of the non-Hispanic Black population in the Minneapolis area in Hennepin County. If you change to quantile breaks, those concentrations become much more explicit. And indeed, we see on the upper end here, these variations that might be more meaningful in this particular capacity. It's kind of up to you as a cartographer to think this through and think about, well, how does this map specifically to what I'm trying to do? There are a variety of other tips and tricks that I encourage you to play around with that are pretty fun. You might be asking, well, how do I figure out how I specify a color palette? Use in the TMap tools package the palette explorer function. I'm going to pull that up here. I don't have it in the code, but if you just copy that over from the slides or type in TMap tools : palette explorer, it's going to pull up for you this interactive color palette explorer in which you can see here for a number of, you can choose a number of colors. You see all of the different color codes you can use. We've got sequential color palettes, categorical palettes, diverging palettes that converge in the middle between a couple different hues, and the Viridis palettes, which are scientifically tested colorblind safe palettes made for data visualization. You can even do blindness simulator to see if your chosen palette's going to be colorblind safe. It's a pretty cool feature. And so we can make some more modifications. I'm going to change my style to Jenks here. I'm going to choose the Viridis palette. And let's take a look at what we get. Using that Viridis palette here, we see the bright yellows are showing up as the greatest concentration. And we can even see by adding this legend histogram with legend.hist equals true, we can see the distribution of values and the mapping of colors onto that histogram. So for exploratory visualization and analysis, with just a couple options changed, you can get up and running, making some interesting graphics. Now, in many cases, you might not want a choropleth map, and there are a lot of other types of maps that you can work with. If you're coming from a GIS background, or indeed even if you are sort of an avid consumer of maps in journalism or in various publications, you might be familiar with something called a graduated symbols map, where in a graduated symbols map, instead of using color to represent a statistical quantity of interest or an attribute in your data, we use size. This is implemented in TMap with TM bubbles. And we can use this code here to take a look at, and we're going to map counts here now instead of percentages. We can take a look at circles in this particular case with the TM bubbles function. We look at circles that are scaled in relationship to the size of the non-Hispanic Black population in a census tract, and we'll overlay it on top of the actual polygon boundaries so we can see where they are. And you'll get something that looks like this. So a different type of representation of your data. And we can run that through over on the R side to see what that looks like. Lots of other options are available for you in TMap, including more advanced map types. One of the reasons why using long form spatial data can be handy is to allow for faceted visualization. We touched on faceted visualization a little bit last week, but a faceted map is also known as a small multiples map, where you show multiple maps side by side for different variables of interest. And when I have long form spatial data, I can use this TM facets function with the by argument here. And I say, facet my map by the variable column, which is saying, give me a separate map for each unique value in the variable column. And we have 5. We have non-Hispanic white, non-Hispanic black, non-Hispanic Native American or Alaska Native, non-Hispanic Asian, and then Hispanic. If we run that code through, and we can pop over to RStudio to do that, take a look at what we get. We get multiple maps, in which case I can look through the various maps of Hennepin County and make comparisons. Hennepin County is predominantly non-Hispanic white, but you'll notice certain areas that have large Hispanic populations. For example, Bloomington, Richfield, and sort of South Minneapolis. We've looked at population, the non-Hispanic black population, but Minneapolis also has a proportionally foreign urban area large Native American population, and strong Asian concentrations in some of the suburbs as well. And we can make these now comparisons across different groups. There are a number of other different map types, and we're only scratching the surface. I'm not going to run through the code on this one because it takes a little bit more time to generate, but one map that I'm particularly fond of, and I like to use in some of my work, I've written about some papers about this too, is dot density mapping, which scatters dots proportional to data values, and is a method that is really good for showing within polygon heterogeneity or diversity. You know, one issue with choropleth maps or showing a particular group at a time is it doesn't necessarily give you a sense of internal diversity, how different groups might live together, and dot density maps can do this. This code is more advanced. This is an advanced example. So if you're new to mapping in R, it might take some time to step through this. If you're a more experienced R user, you'll notice some of the notation we talked about before. The mapdf function is coming up again. And functionally, what this code is doing, just to step you through it, is it's sampling within polygons proportional to the data values. In this case, we're generating dots proportional to about 50 people in each group. And so as it steps through here, it takes the data set, it filters it down for a particular group, generates a new column that represents how many groups of 50 there are in each census tract, samples points. So it basically scatters dots randomly within those census tracts and then assembles all of those dots together. So this is a more advanced code example. I encourage you to fiddle around with it and learn from it. At the end, we use this slice sample function to randomize the order of all the dots, so no one group appears on top of another. And when we do that, we can create dot density maps like this, where you see that there are certain areas like South Minneapolis, Brooklyn Park, that are very racially diverse, and other areas like Southwest Minneapolis and some of the far suburbs that are less racially diverse. There are some limitations to dot density mapping. You'll notice the dots here that kind of conform to the edge of those census tracts. You can see that. And Minneapolis, lakes everywhere, we're definitely putting dots in lakes here. So there are some methods that more advanced users can explore to remove, say, water areas and then generate the dots. These are kind of interesting techniques that when you're putting together this entire workflow are worthwhile to explore. A couple other things before we move into exercises and the last piece here. A couple other features you might be interested in with respect to tidycensus. I used to get this request a lot. Well, I'd like to map the entire country, but what do I do about Alaska and Hawaii? How do I handle that? Do I need to make multiple maps and assemble them? What do I do? So Bob Root, is my collaborator on the Tigris package, came up with a solution. He wrote a package that's really a data package called Albers USA that creates US state and county geometries, but with Alaska and Hawaii shifted and rescaled south of Arizona in ways that you'll often see with thematic maps of the United States. And I incorporated this into tidycensus with the argument shift geo equals true. So check out what we can do here. Let's make a map of median age by state with Alaska and Hawaii shifted and rescaled. I'm going to jump back over to R and let's try that out. We'll grab the data. We get the warning message here. Alaska and Hawaii are being shifted and are not to scale. So Alaska appears a whole lot smaller than it actually is, just so we can see it adequately on the map. If I run through this code here, just to plot and see what it looks like for a basic plot, you'll notice that we get a visually appealing Albert's projection of the continental United States, and then Alaska and Hawaii rescaled and shifted so that we can see all the 50 states plus DC at the same time. We can then map our data using the same methods that we've just learned with respect to TMAP. So let's go ahead and run that through. And here we get a choropleth map that's showing median age by state, where we can actually see Alaska and Hawaii. Even though they are shifted and rescaled, we can see them with respect to and in comparative perspective with the other US states. And so median age, we talked about median age last week, how we analyze our data in that capacity. We look at a population pyramid of Utah. Utah is the youngest state by median age in the United States. The oldest state is Maine. And you can see some of the older states include Florida and West Virginia. Younger states include Texas, but now we can much more easily compare Hawaii and Alaska with the other US states. So Shift Geo is available for states and for counties only. It's not available for other geographies at this time. A couple other final pieces that I want to leave you with before we move into hour 3. We don't really have time to get into interactive mapping in R, but I strongly encourage you to look into some of the packages that are available for interactive mapping. I mentioned in the first hour the Leaflet package, which is probably the most popular R package for interactive mapping. It works great with the Shiny framework for reactive programming and data dashboards, which some of you may have heard of or use. And additionally, I'd strongly encourage you to look at the Map Deck package, which is an interface to the Mapbox GL.js library through Uber's DeckGL. If that's sort of a technical mouthful, your takeaway with MapDeck is really fast, high performance interactive maps. I would strongly encourage you to take a look at MapDeck. If you don't want to get into any of that, use MapView. MapView has an argument zcall that allows you to specify a column in your data set and make an interactive choropleth map right away. Let's say we want to look at our DC income data. I'm going to go back over to the code here and I'm going to run this through. Simply by specifying zcall equals estimate to represent the estimate column in my data set, check it out. I have an interactive browsable choropleth map where I can hover over any census tract and get the median household income estimate. I can click, I can get some more information about that place and explore variations in DC. So if you want to do exploratory choropleth mapping, MapView gets you up and running very quickly. The last piece before we move to the break, what if I still want to use a GIS? That's okay. I don't mean to denigrate GIS at all. I do a lot of my work in R, a lot of my mapping in R, but one thing that is very difficult to replicate on the programming side of things is just that manual touch that a GIS allows, where you can open up a layout, move around map elements, resize them manually, and get it just right for presentation. For those of you with a graphic design background, something you might do in Adobe Illustrator as well. And so you say, well, okay, I did my data wrangling work. I grabbed my data in R. How do I get my data out so that I can use it in ArcGIS or QGIS or Tableau? Use the SF package and its function stwrite. It allows you to write out your R object to a spatial data set of choice. For example, this code that I have up here on the screen writes it out to a shapefile, and you can then grab that shapefile, load it up in your geographic information system of choice, and make your map over there. So it allows for an integrated workflow in that capacity. All right, that's what we have for hour 2. So let's take another 10-minute break or so. We'll come back about 5 after the hour. And in the meantime, try making your own map with TMap. It doesn't need to be extraordinarily complicated. If you're just getting started, repurpose the examples. Maybe take the DC income example and try making a map using that data set in TMap, or copy my code for Hennepin County and make another race and ethnicity map. Maybe change the county or the state if you want to, and play around with the colors a little bit. If you're feeling comfortable, so for more advanced users at this stage, go find another variable in tidycensus and map that one instead. So go try out TMap. It's pretty fun to work with. You can get up and running pretty quickly, as you've seen, but if you're an advanced user, there are so many options. We've barely even scratched the surface of what you can do. So yeah, let's take a little break. We'll come back around 4:05 and do a little Q&A on this section, and then get into our final topic, which is spatial data analysis and GIS workflows with the SF package. All right, welcome back, everyone. Let's get going with hour 3, but before we get started, JP has a few questions so that we can chat about.
Yeah, Kyle. So we've had some questions that continue, actually some questions that we got late last week as well. And there's a lot of interest for those who see some of the interactive maps you're creating,
Yeah.
who really want to be able to kind of bring these outside of R or somehow embed them. Is there any way to do that?
Yes, there is. So a couple different ways to do it. And I don't want to get too heavy on the details here, but I'll show you some options. So here I have my interactive map in my RStudio viewer. A few things I can do. I can use this publish button to click publish HTML. What this will do is, if you would like to sign up for it, RStudio has a service called RPubs that's free, and you can publish it directly to that account, and it'll put it on an RStudio hosted website that'll host that map. So that's one option. Another option is you can choose export save as web page, and that will export out the web page and the assets that you need to get that to work. The safer way to do it, I have found, is to take your map object and assign it to a variable. So I'm going to type here, I'm going to call it M1, and I'll assign that to a variable. And then I'm going to use the HTML widgets package and a function in it called save widget to save out my map. And you might be saying, HTML widgets, save widget, what does that mean? Under the hood, there's a package called HTML widgets, which you may not be familiar with, but it provides the framework for most of the interactive data visualization packages in R. It was invented several years ago by some really talented developers who sought to create a streamlined way to take interactive JavaScript charting libraries, so all of those cool web visualization libraries that web developers are using to make interactive content on websites, and bring them to R. And the interactive plots that I've shown you over the past couple weeks are leveraging this functionality under the hood. So if I run HTML widgets and I run the save widget function, I can specify the widget, which is going to be my interactive map object, which right now is called M1. I then specify a file, and I could call it whatever I want, DC income map.html, because I'm saving it out as an HTML web page. And I'm going to keep the other options as they are. Self-contained equals true. In many cases, that'll be what you want, because that will try to, as much as possible, store all of the JavaScript assets in one file, as opposed to scattering them across folders. So I'm going to go ahead and run that. And I might need to fiddle with it a little bit more, because we're doing some on-the-fly coding here. But basically, this is the workflow that you'll tend to follow. So if I had a little bit more time, I'd debug that error message, but I would encourage you to look into that a little bit more. So those are going to be the options that you can try.
Great. I think that'll make a lot of people really happy. I know that's been a question that we've seen multiple times today and came up a lot last week after the last hour.
Yeah, definitely.
So we have a few other questions. One of them had to do with when using geom_sf. Mm-hmm. Does the data need to have a column named geometry?
Yes and no. So basically, just to refresh, we were using traditional ggplot syntax to specify here the data set and an aesthetic, and then making our map. So let's go ahead and pull that up here. RDC map. So when I'm running geomsf like this, yes, it does have to have a geometry column named geometry. But there's some alternative ways to do this if your geometry column is not named geometry. In most cases, it will be, but in some cases, it won't be. If I were to change this and move this information down here and specify explicitly inside of the geomsf call, data equals DC income, aesthetic is fill equals estimate, and I can run that through. Now, my geometry column is still called geometry. That would still work even if the geometry column were not named geometry. Alternatively, sort of the third option is you could specify, let's say your geometry column is called geom. You could specify explicitly as an aesthetic, geometry equals geom, or whatever it is that your geometry column is called. That will also work. So those are the three ways to do it.
Great. All right. Is it possible to display more than one map layer using a map view?
Yes, absolutely. So let's. This is actually good. This is actually going to work. So we created our landmarks right before. So I have our DC landmarks. So those are all our DC landmarks, and you might want to say, well, I want to display all of those landmarks on top of a map of DC income. If you use the plus operator, you can link together multiple map view maps and layer them on top of one another. So try this. I'm going to do map view DC income zcall equals estimate plus map view DC landmarks. And look at what I get. Now I have all of the landmarks sitting on top of my income data, and I can kind of interactively browse them. And map view has all sorts of functionality built in that we haven't even talked about yet. You can choose a different base map. If I want a dark base map, that's a click away. If I want a satellite imagery base map, that's a click away. If I want to turn on and off my layers, that's built in as well. So it gives you that GIS data viewer type functionality out of the box.
Great. So you might recommend, though, if you were to draw multiple choropleth map layers, you might take advantage of that kind of checkbox to draw one at a time rather than multiple choropleth maps at once.
Yeah, you could do that. Absolutely. So, and you could also use that that leaf sync function I demoed earlier to create synchronous maps as well, if you'd like. So there's a lot of interesting options there.
Yeah.
And MapView is another package that has more options than I even know about. So you can really dig in. You can do a lot of pretty sophisticated stuff with it.
So this might actually go back to what we were just talking about with the multiple layers, but would you advise factoring in the margins of error into the estimates for thematic maps? Is this an important step, do you think? And if so, how would you display it?
Yeah, that is a really good question. So there's been a lot of research about this because, as we know, margins of error vary significantly, from place to place, and there isn't. It's difficult to show that on a map. I've seen some research that has suggested trying to display either used bivariate choropleth maps, which is implemented in in some other packages, to display that. I've seen some research suggesting modifying the transparency of the polygon fill. So you have sort of more transparent colors for areas that have a greater potentially margin of error and less transparent for estimates that you're more confident in. But you know, that's an excellent question to think about. There's some other interesting methods. If you go to the tidycensus documentation, that'll actually speak to one of the methods we'll talk about in this last hour, where there have been studies that have proposed doing something called regionalization, which you'll actually learn how to do in about a half hour, to aggregate up different shapes to try to get a smaller margin of error relative to the estimate, and then end up mapping that so that you know that all your shapes have reasonable margins of error relative to the estimate. But it's not a solved problem with respect to visualization. What I would probably tend to recommend, you could look at those different methods for visualization at the risk potentially of confusing your viewer, or make sure again that you potentially could use multiple visualization types, or really kind of take seriously thinking through what it is that you are showing, and if what you're showing is a reasonable thing to map. That's something that maybe is an unsatisfying answer, that less piece, but if I'm making a choropleth map of kind of the percent of children under 5 living in poverty, my margins of error can be really, really high. And if I'm showing that by neighborhood, the patterns that I'm showing might not necessarily be patterns that are statistically reasonable. And so that's something that, as an informed user of ACS data, that is worth reflecting on before you're presenting your information.
Great. We actually have somebody who's posting in the chat as well at the same time, just talking a little bit about thresholds and some other ideas to think about when looking at margins of errors and doing things like calculating the coefficients of variation. So things that are very useful to do. So thank you for discussing, the concerns that we should have when looking at the statistical accuracy of the data, the precision of the data.
Absolutely, that's a great point. There's a lot of really interesting research on the topic that, for those of you who are interested, I'd strongly recommend checking out.
All right.
All right. Well, let's delve back in. We got about. Sorry, JP.
I'm sorry. I was just saying that I think that's all the time we have for questions right now. Why don't we turn things back over to you for the last hour?
That sounds great. All right. Well, we've got about 40 minutes left, so let's dive right back in and take a look at our last topic for today, which is going to be spatial analysis of US Census data with the SF package. And going back to, as we've done for the previous 2 sections, what do you typically do sort of in a GIS context? You could pull up a data set or something like that in, say, a QGIS, and you've got all sorts of menus that are available to you. All of these menus at the top of the screen: vector menu, raster menu, plugins. If you have QGIS up, what that'll show, and indeed I might actually just pull that up on my computer real quick so I can illustrate that interactively. So here we go. Here we have QGIS. We look at our different menus. I'll click here on the vector menu, and we see all sorts of different tools. And those tools, if you come from an ArcGIS background, they'll be found in Arc Toolbox. But those tools allow you to do GIS operations, and that's often where some of the power of working with spatial data comes from. Having representations of data, mapping data, that's powerful, but we can also use the spatial properties of the data to perform analyses and draw conclusions. And so here we have geoprocessing tools, buffer, clip, dissolve. I'll talk about what some of those mean in a little bit, but they allow for manipulation of geometries, a variety of different geometry tools, analysis tools, research tools. And so these will be named a little bit different in QGIS than they might be in ArcGIS, but there are analogous methods for this across these different desktop GIS platforms. And so we can think about a variety of common tasks that we perform in a GIS context. Select by attributes. That's one of the biggest methods that I always used to use when I used ArcGIS on a day-to-day basis. I want to know what are the neighborhoods that have a poverty rate above 30%, and I want to highlight them on my map. Select by attributes allows you to use what is analogous to a SQL query to subset your data accordingly. Select by location. That is where you take two or more layers that sit on top of each other, two spatial data sets, and think about how do they interrelate spatially. For example, you might ask a question like, here I have this circle that represents, or this buffer area that represents 3 miles around my store. What are the census tracts that are within 3 miles of my store? That is accomplished with a select by location query. Spatial joins take this one step further and think about merging data together, joining data based on spatial location. Like, for example, what is the average income of census tracts within 3 miles of my store? That's something that can be accomplished with a spatial join. And then finally, we looked at those different tools, which are in an ArcGIS context called geoprocessing tools. So clipping data, which is using one shape as a cookie cutter to cut out an area of another shape. Dissolving data, which is looking at common attributes in a data set and merging together geographic features based on those common attributes, aggregating up attributes in the process. And you have unions and erase tools, intersections, there's a lot. The SF package is more than just mapping, it's more than just data representation. It's a tidy data model to do all of this. It brings all of your favorite tools from the tidyverse, or at least many of them, to GIS workflows. And some of these methods, some of you may be familiar with, others you might be less so, but it's really, really useful. And I'm going to illustrate how to work with spatial data in that capacity over the remainder of this workshop. So a couple of things about the SF package. Its data model, it's designed explicitly for integration with the tidyverse, which means that many tidyverse methods are implemented in SF and allow you to work directly on SF objects. We've actually already done that a little bit today. This is important. Geometries are sticky. What does that mean? It means that if you run a method on an SF object, you keep the geometry without having to explicitly say that you're keeping it. So it knows that the data is spatial and you want to keep that data as a spatial object. And then beyond that, there's a whole family of functions with the ST underscore prefix. For those of you who come from PostGIS or a database background, you may be familiar with this. But that family of functions, they help you complete a whole lot of common GIS tasks using the GEOS library under the hood. So let's take a look at how we do this using a very timely and applied example. I live in Fort Worth, Texas. This is something, of course, that's in the news every single day, wherever we are, really around the world, but certainly here locally for me. And so it's of acute interest. How do COVID-19 vaccination rates vary geographically in Texas? So to figure this out, we have to look at a couple of things. We might be interested in county level data, but that's often very coarse. And if you're looking at disparities within some of the large cities of Texas, like Houston or Dallas or Fort Worth, county level data is going to mask that over. You're going to be less interested in that. The most granular geography at which we can get vaccination data is the zip code. And for those of you who are a seasoned spatial analyst, you might be saying right now, whoa, hold on a second. Zip codes aren't real geographies. They're just routes defined by the post office. And how can you do actual spatial analysis with zip codes? You're right. That's all true. I tend to be on the side of some information if it allows us to understand our data in a deeper way is better than no information, so long as we're appropriately aware of the caveats. That's my attitude towards margins of error in the ACS. Use your data, but be informed of what it means. It's the same thing with zip codes. So zip codes, for a little bit of background, especially, for maybe a non-US audience, or if you haven't worked with spatial data much before, are basically codes that are used by the United States Postal Service to deliver mail. Zip codes themselves do not have geographies, and any geographies that they have are not released by the Postal Service, but a lot of data is collected at the postal code or the zip code level. And so what the Euro does is they create geometries that approximate zip codes called zip code tabulation areas. These are not zip codes, but they're built from census blocks in which the Census Bureau will look at a census block and take its address file and say, what is the most common zip code of addresses in this census block? And then it allocates that census block to the appropriate zip code tabulation area, allowing for rough approximations of zip codes spatially, which are useful in that the most granular geography for many different applications, often health data, is the zip code. And so we're going to use zip code tabulation areas to map the distribution of vaccines and vaccination rates across Texas with those caveats in mind. Additionally, when we're thinking about how COVID-19 vaccination varies in Texas, we're going to need to normalize that by population, which means divide it by an appropriate denominator, because zip code tabulation areas vary widely in population, from ZCTAs or ZICTAs that have almost no people in them to tens of thousands of people. So we're going to need to adjust that appropriately. And fortunately, we can use tidycensus to do that. So a couple of things to get started. I have downloaded and cleaned up a data set for you from the Texas Department of State Health Services. It's accurate as of March 2nd. I think they were going to release a new data set today, but it wasn't up from what I saw before the workshop. It's available as a pretty nicely formatted Excel spreadsheet, but I've cleaned it up and saved it out as an RDS file. If you're not familiar with RDS files, it's a binary data format, kind of a compressed data format that you can use with R. This file, if you cloned or downloaded the repository from GitHub, is in the folder specified on the screen, in the data folder in the spatial analysis subfolder. If you're using our Studio Cloud, it's simply in the data folder. And I adjusted the code there appropriately, so you should be able to read it in. If you're not able to read it in, just make sure you have the path to the data set correct. So I'm going to jump back over to R, and we can take a look here as I scroll back down and take a look at our data. So if I go to files here and click data, I have the raw data file. I didn't commit that up. Well, I might have actually, but I have the raw data file here as an Excel spreadsheet, which you can actually go and download yourself from the link provided if you want in the slides. But I have the cleaned up data set here. So if you did clone that repository, it should be there. So let's go ahead and read that into R and take a look and see what we get. So we have a data set with 4 columns. Let me make this nice and visible. And around 2,500 rows. So we have the zip code. We have the total number of vaccinations. What that refers to is the total number of people that have received either a first dose or fully vaccinated. So for example, for the Pfizer and Moderna vaccines, for full vaccination, they need 2 doses. For full vaccination with Johnson & Johnson, which I don't believe we're doing here in Texas at the moment, it only needs the 1 shot. So the column that we're going to be most interested in is total vaccinations, because it's anybody that's received at least 1 shot. Now, granted, that doesn't refer to fully vaccinated, but something that does come up is that small numbers are suppressed. For example, below 5, you'll see that with NAs. So total vaccinations, so total number of people who have received any number of shots, that's going to be our most complete column. And so we're going to work with that one. in this particular workflow. So let's think about the general workflow that we need to accomplish. Here we have zip code level vaccination data, but we're missing a few things. We want to map and analyze the geographic distribution of COVID-19 vaccination rates by zip code tabulation area. There's a few things I don't have. I don't have zip code geometries or ZICTA geometries in this data set. All I have is the zip code. And I can't calculate a rate right now because I don't have appropriate population data. All I have is the number of total vaccinations. So I'm going to need to reach out to a different data set and then assemble a data set, which we haven't done yet, to get to where I need to go. Fortunately, we can grab a lot of this data in an integrated fashion with tidycensus. So given that vaccines are right now only being administered to people age 16 and up, let's grab some population data for age 16 and up. We'll grab from the ACS data profile using the variable code DP030001. We can get it at the ZICTA geography level, get geometries, specify state equals Texas, which is a new option that's available as of the 2015 to 2019 ACS. Census wasn't distributing ZICTAs by state before then. And that pulls down zip code tabulation area geometries with linked population data, as you can see here on the map, for the state of Texas. So now we have our normalization data and we have our geometry thanks to tidycensus. So let's jump back to R and let's run that through. So here we go. And as you can see here, this is a basic choropleth map mapping counts. I know I said not to do that, but it's just for a quick look at our data. You'll notice that some ZICTAs have hardly any people living there, and then a few, especially around the major cities in Texas, specifically in suburban areas, you'll have upwards of 80,000 people. So we really need to normalize if we want to get an accurate representation of inequalities in, say, vaccination rates across the state. So how do we go about doing that? Let's take a quick glimpse at our data. So here we look at our data for vaccinations in Texas. Our column types, when we use the glimpse function, are shown. Zip code is character string, and the other values, those are of type double, so they're numeric. Let's take a quick look at our population data from tidycensus, which is called POP 16 up. We see here that we have some columns that might align that we can work with. Our ACS estimate is of type double, so it's numeric, so we're ready to go in that capacity. And we notice here we have this column called GeoID. And again, in tidycensus, every data set you get with tidycensus has a GeoID. It's a unique census ID code that can be used to, again, uniquely identify that particular geographic unit. If you've worked with databases, if you've worked with GIS, or indeed just worked with tabular data in R before, you might be seeing where we're going with this. We need to figure a way to assemble these data sets, put them together, and then calculate a rate. So our first step is going to be a join. We're going to do a join operation. And a join operation in a database or a table context is taking columns that have values that you can match in two different tables and then matching them and merging the data sets together based on matching values in one or more key fields. The way we specify that in the tidyverse is by using the left join function. As mentioned, SF objects can be used with tidyverse functions. And so what we're doing here is we're saying, using our pipeline operator here, take my population age 16 and up data set Then perform a left join, which basically means join all of the matching information from a data set to my original data set, join data from my Texas vaccinations data set, and then with the by argument here, we specify how we're going to do the matching. The GeoID column represents the zip code, or in this case, the ZCTA value in our population data, whereas the zip underscore code column represents the same value in the vaccinations data. So we specify by GeoID equals zip code. That's how we're matching. Once we do that, we can calculate the rate by using the mutate function in dplyr. I'm creating a new column called percent vaccinated that's calculated as 100 times the total number of vaccinations divided by the appropriate denominator, which is the ACS estimate in this case, which is the population age 16 and up. Finally, I'm doing a little bit of data cleaning. When I was exploring this data, I saw that there was some percentage values that well exceeded 100. Of course, you know that can't be true. You can't have more than 100 people getting vaccinated, 100% of people getting vaccinated in a zip code. That's not logical, but when you browse around and look at it, one of the places that popped up was a hospital district in Houston. And oftentimes you'll see this when working with public health data by zip code. We're just grabbing and, the Texas Department of State Health Services acknowledges these caveats. It's, often it's workers who they're writing in the zip codes, they're collecting the data sometimes, they're doing the best that they can. But if someone comes in to get vaccinated and they don't provide an address, oftentimes someone will write down the address of the hospital itself where the vaccination took place or the zip code of the hospital. And so we saw some areas in Texas that had way more vaccinations than actual people that lived there. And so I'm just converting all of those to NA because in this particular workflow, we're not going to go down and investigate that further. So we're just going to convert that over to NA for purposes of illustration here. Let me run that through and we can take a look at what we have. Now I've got matched columns and percent vaccinated. So this particular 75973, percent receiving at least one dose, a little over 20%. We can map that information using tmap. Using the same syntax that we just learned, we're going to use palette equals reds. We're going to do sort of a light red to dark red color palette, and we're going to map our ZICTA areas with the percent vaccinated column, and let's see what we get. Now we've been able to visualize that. So we're well on our way here. It's a little bit tricky of a map to interpret. This is something where those zip code tabulation areas, there are going to be certain areas, especially out in far west Texas, where it isn't even covered by an area because nobody lives there. And indeed, you have very dense areas within, say, Dallas, Fort Worth, and Houston that you can't really see when you're zoomed out on the entirety of Texas. But this is a good first step. So now what we want to do is start thinking about spatial analysis workflows. And we're going to step through these different pieces that I talked about before. Selecting data by attributes, selecting data by location, spatial joins, and geoprocessing. So selecting data by attributes, we use the filter function in dplyr. This works on spatial objects and then gives us back a spatial subset or a subset of spatial data. Multiple ways that we can do this. The string R package, if you're not familiar with it, I'm using, we talked about it a little bit last week. It has a lot of great functionality for string manipulation and extracting information from strings. Let's say I only want the zip codes around the Dallas area. I can say, give me back only those zip codes where the first two characters, so I'm using str_sub, the first two characters of the GeoID column are 75. So I'm querying my data accordingly and subsetting it down. I can then query further and say, take my Dallas area shapes and then filter it for only those areas where the percent vaccinated value is equal to or greater than 40. We can map that out and let's see what we get. I've now filtered my data down for only those ECTS that start with 7.5, and then I layer on top of it in navy those areas where the percent vaccinated is above 40. Now this map kind of looks like a bit of a blob, which is understandable, but something that I want to bring up I don't have in the slides. You can use map view on objects like this too. If I want to say, well, what are some of the areas that have high vaccination rates? Maybe I type in map view above 40 just to take a look at it. And then I can explore interactively. So we look here in the Dallas area. Interestingly, as so many things are, it's the wealthiest neighborhoods in Dallas that have the highest vaccination rates. And then you have a few areas out here in Tyler and then out in the northeastern part of the state that have zip codes that conform to, that query that we put in. So use map view in your spatial analysis workflows as much as you can. The next example that I want to show is thinking about spatial overlay. How do I use multiple layers or multiple spatial data sets together? For example, a common question that you'll hear is, well, how do vaccination rates vary between or within metropolitan areas? And I want to show a couple methods that we can use to accomplish this. The first is going to be analogous to a select by location operation in a GIS context, where you have one data set and you're interested in finding information in a second data set that overlaps that first data set. We can call this in SF context spatial filters. We also might be interested in using a method called a spatial join, which actually merges together information from two spatial data sets based on their spatial relationship. If you're looking for, say, information about a particular metro area, use tigris for that. Tigris's core-based statistical areas function allows you to pull down metro area boundaries. Here, I'm grabbing just the Dallas-Fort Worth metropolitan area. And so let's take a quick look at that. I'm going to pull this down. And let's map view it just to see it. So this is the boundary of the Dallas-Fort Worth metropolitan area. So the next question is, well, I'm interested in grabbing the zip code tabulation areas that are in the Dallas-Fort Worth metropolitan area. How do I do that? It's fairly straightforward using SF, provided that your data share a coordinate reference system. This is essential or else it won't work. They have to be referenced to the Earth surface the same way, but they are in this particular case because we're grabbing geometries from tigris and tidycensus for starters. So in this particular example, we can use a couple of different methods. The SF package implements spatial filtering in this particular case using both base R notation, so bracket and indexing, similar to how you would work on another type of R object or on a matrix. Or you can use a more tidyverse style ST filter function where you say, filter the first object for areas that intersect the second object. Let's take a look at how that works. I'm going to run this through. I'll need to load the SF package, and I'm going to run this through. We can make a quick map. And here I'm using tmap to show the zip code tabulation areas in the Dallas-Fort Worth region, color-coded by the percent of the population that's received at least one dose. this is great. You might be interested in using map view instead. Or interestingly enough, you can use in tmap mode view. This is a little bit of a trick in tmap that's pretty fun. So if I do tmap mode view and run that through, note the message I get. It says tmap mode set to interactive viewing. Now, if I rerun through my tmap code, check it out. My map is now interactive and browsable using Leaflet under the hood. And so this is something that's a really fun trick. Map view is great. I use it all the time, but also tmap, if you like that syntax, you can specify a tmap map using all of the options that you're learning today. And then in this particular case, I can fiddle around. I can choose, say, OpenStreetMap. If I wanted to, I could have, modified the fill transparency of this, but it's interesting. You go over here. This is the Highland Park area. I click, I get a little pop-up in Dallas, which is one of the wealthiest areas in the entire region. It's also one of the older areas in the region. So a lot of people there are getting priority for vaccines, but still we're showing 83% vaccinated. And you can see some of the inequalities that exist. Parts of, say, South Dallas, under 20%. What this process relies on is something called a spatial predicate. The question, how do we identify which zip code tabulation areas intersect, so to speak, or within the DFW metro area? The default spatial predicate used in ST filter is ST intersects, which says if any part of one spatial data set overlaps the other, then what we have is an intersection, and that's what we'll return back. There are many other spatial predicates that are available. I'm not going to run through this code for purposes of time, but for example, we can specify with the dot predicate argument a different spatial predicate. If you want only, say, those zip codes that are entirely within the DFW metro area, you can specify, say, ST within, and it gives you back something that looks a little bit different, because the overlapping zip codes on the outside, or zip code tabulation areas, those have now been removed. So you can try running that code if you like. And I won't say an alternative to a spatial filter, but a cousin to it is a spatial join, which you can think of as analogous to a table join. But instead of having a key field, the linkage between the two data sets is the spatial relationship, the spatial predicate. So a spatial join is a very common operation in a GIS. It joins information from one spatial data set to another based on shared spatial relationships. And we can implement spatial joins in the SF package with the st_join function. In this particular example, what I'm doing is I'm grabbing metro boundaries for the 4 largest metro areas in Texas: Dallas, Fort Worth, Houston, Austin, and San Antonio. I'm then using a spatial join to attach that metro information to my zip code tabulation areas, so that I know for all of those zip codes that intersect those metro areas, what their metro area is. I'm specifying here left equals false. This is computing an inner spatial join, which means that any zip code tabulation areas outside of these 4 metro areas will be discarded. And so just for a quick illustration of what that's doing, I'm going to run this through. And if I want to plot it real quick, I can do that. So these are the areas that I get, any sort of intersecting areas. And then we have some zips, interestingly enough, that overlap both the Austin and the San Antonio. And so they'll be allocated in this particular instance to both. If that ends up being sort of an issue, that's something that can be covered in this instance. In other workflows, and you can identify, for example, using SF, the largest shared overlap, that's something that you can work with as well. So we're just looking for purposes of illustration here. From there, what's interesting about this is we can start doing comparative analysis. And this is an example, if you're asking the question, okay, looking at the distribution of vaccination rates within these different metro areas, how do they compare with each other? So we could draw histograms, or in this case, I'll draw a density plot for each metro area and use ggplot2 faceting to make a comparative visualization. Going back to the code, we can show you what that looks like. And we see here a comparative visualization that wouldn't have been possible without the spatial analysis component. We attached the geographic information about the metro area to the zip code tabulation areas, and now we can look at the distribution of vaccination or vaccination rates across zip codes in those different metros. And so what we see here is that the shape tends to be fairly similar. Austin, you can see where the peak is. It's a little bit more to the right. So Austin's doing a little bit better vaccination-wise than Houston is. But across the large metros in Texas, overall, it's fairly similar. So this is a pretty interesting way to compare different data distributions for information that might not be necessarily directly embedded. So looking at the time, we're coming up against time a little bit. So I'm not going to step through this last example in tremendous detail, but I encourage you to play around with it. It's really fun. The last example I wanted to show is an advanced application that really can get you thinking about how do you put all this together and do analytic workflows that could be applied in a variety of different applications or industries or government or what have you. It involves spatial clustering and group-wise spatial data analysis. And it uses the SPDEP package, which is beyond the scope of this workshop, but it's really a great package to learn. It's your workhorse R package for exploratory spatial data analysis and spatial modeling. It allows you to identify for any spatial element of your data, say a polygon, what are its neighbors? What are the, say, census tracts around a particular census tract, which ends up being very important because if you're doing, say, regression modeling on spatial data and you're not controlling for or accounting for spatial autocorrelation, you're going to get a misspecified model. And so SPDEP really helps you out with that. For purposes of time, again, as I said, we're not going to step through this in tremendous detail, but what you'll see in this example is using an algorithm called Skater to perform something called spatial clustering and regionalization, where you might have a question, say, I have a bunch of census tracts in a geography of interest. Can I define relatively coherent and spatially contiguous zones that all border each other and are relatively similar demographically? You might be thinking about sales territories for a business application. You might be thinking about, interestingly enough, an application with respect to political redistricting. This is another potential application. And so I'm not going to step through the code in tremendous detail, but what you'll see in this particular example is taking three variables. Here we have median age, median income, and percent of the population over 25 that's finished college. We can implement the Skater algorithm to ultimately identify relatively coherent regions based on those inputs, and those regions will be spatially contiguous. So for those of you who are familiar with unsupervised machine learning, and a popular algorithm is k-means. You can use k-means on a spatial data set and get clusters, but those clusters won't necessarily border each other. They might be scattered around a metro. So here for Wayne County, Michigan, what we're doing is we're identifying spatial clusters, so clusters that actually border each other. In this case, we have 7 groups. What we can do from there, and this is the last piece I want to show, the group by and summarize functions in dplyr. To do group-wise spatial analysis will actually summarize the geometries as well, performing something analogous to a dissolve operation in a GIS. So given that we've assigned a cluster group to each census tract in Wayne County, we can roll that up and dissolve the interior boundaries of the geometry and actually get regional polygons, which is pretty cool. From there, we can aggregate up information and start to kind of do, again, redistricting analysis or sales territory analysis, or if you're looking at kind of resource allocation in a city, there are all sorts of interesting applications of this method. So try running the code for yourself and see what you get. All right, I do have some exercises that I'll leave you with to continue your learning, given that we're just about out of time, but I would encourage you to play around with this. If you're comfortable with the GIS, again, what you can do using the tools you've learned today is use it as a data portal. Instead of having to go to the websites and assemble your data, pull in your data using R, write it out, and then load it into Tableau or ArcGIS. Or if you're comfortable or you want to try it, the SF package allows you to do a lot of the GIS tasks that you would normally do in a day-to-day workflow entirely in R. And we've shown a few examples of how to do that. And indeed, the spatially constrained multivariate clustering tool in ArcGIS uses the same algorithm that I just stepped through there, the scatter algorithm. So a lot of what you can do on the GIS side of things, you can also do that in R. So I'll leave this slide up for a little bit if you'd like to play around with some exercises. Otherwise, thanks for sticking around until 5 o'clock today. Thank you so much, JP. Thank you so much, Bill. It was really fun to step through this. And in 2 weeks, I'll be back talking about microdata. So individual level microdata using tidycensus from the American Community Survey. And there's gonna be some bonus material that should be fun in the last hour. So I'll look forward to that.
Sounds great, Kyle. Thank you so much. Really appreciate it. We went through a lot today, answered some great questions as well. In the chat, I'm quickly going to throw in a link that includes the resources that Kyle used today. I also want to just highlight, I know that a few of you were using the R Studio Cloud and wanted access to the specific code, so that way you can kind of pull it if you wanted access to it later. In the chat, I'm also putting the URL to actually go to the code that Kyle used today. So if you ever want to go back to it, it's on GitHub. I encourage you to go to his GitHub site, which the link is actually on the resources page we posted as well. And finally, I just want to remind you all of the upcoming webinars that we have. Next week, we have a webinar for especially targeting educators on integrating census data analysis into especially substantive courses. That will be with a different panel. We will again have Kyle back on March 25th to talk more about analyzing census microdata in R. So again, you can use the links that I sent, the ssdan.net, the webinar resources link. That will provide you with the links to register for each of the webinars, as well as the resources we used today. And when the videos are available from today's webinar, we'll post those videos there on that page as well. Thank you everyone for attending, and have a great day. Thank you, Kyle.
Thanks everyone, appreciate it.